Greetings and welcome back to a new video about DC series motor. This is our example number 4. In this example we will discuss another problem. So let's move on. We have a DC series motor and it requires a terminal voltage of 260 volts. It draws a current of 40 amps when the shaft speed is 100 radians per second. In addition, we know that the armature resistance is 400 milliohms and also the field resistance is 500 milliohms. The friction torque for this case is 4 Newton meters and it is independent of the shaft speed. Okay, what are the required calculations? Calculate the shaft torque for this situation, and in question B we want to change the shaft speed using a series resistor which is placed in series with the motor. So we have then the new question: calculate the required series resistor, which is just called Rx here, to reduce the speed from 100 radians per second to 50 radians per second, while the shaft torque and also the terminal voltage are unchanged. So what we have calculated in question A must be the same, and the given terminal voltage is still 260 volts. Okay, how do we start? Again, looking at the solutions, we start with a model. And a model for a series DC motor is shown here again. We have the terminal voltages, the field part with its own resistance, and also the winding inductance, and also for the armature in a similar form. And this is our back EMF voltage, which is then driving this rotational speed. Okay, let's look at our first calculation, which is then the shaft torque, and we know also in addition that the series combination will allow us to say that the terminal current is equal to the field current and also the armature current. So that is actually a very useful condition here. Shaft torque, which is called just T sub S, that is actually the developed torque minus the friction. So we lose some torque due to that friction, and that goes to the actual shaft. So what is then a developed torque? Developed torque is given by this expression, which is then the motor constant times the armature current. So if I look at these two equations, the final goal is of course the shaft torque. I need the friction torque, which is already given, but I also need the developed torque, which I then require the motor constant, which is not given. We have of course the current, so if I just substitute this in this expression, I still have one unknown left in order to calculate the shaft torque. So we still need to go to the motor constant. So for that we can develop of course again our voltage equation here using Kirchhoff voltage law. This terminal voltage will now be across these 5 elements again, so the back EMF plus these 4 components. And then we know, since this is a DC operation, we can say this is all 0 because the reactance of these inductors will be 0. So we can just leave them out. And then we have a more simplified form. So the terminal voltage will be the back EMF plus the terminal current or the armature current times the summation of these two resistors. Now we know the given values here, except of course the back EMF, so we can just now calculate the back EMF voltage, and that is then for this condition 224 volts. Now what is the next step? The next step is actually calculating our motor constant. We know this back EMF is also related to the motor constant by this the shaft speed. We know the shaft speed for this condition. We also know the back EMF voltage, so we can calculate now the motor constant. And let's just substitute the values of the given value for our rotational speed, the shaft speed, and also the calculated back EMF. We now have 2.24 Weber, so that's our motor constant. Okay, now we are very close because now we can calculate the developed torque just using this formula. 2.24 times 40 will give us 89.6 Newton meters. Now we have now calculated the developed torque, so we are very close to the final value, which is then our shaft torque. Shaft torque will be then the developed torque minus the friction. We know the developed torque, we already given the friction torque, so we just substitute the values. You will get 85.6 Newton meters. That's for question A. Okay, let's go to question B to calculate the required series resistor. So, and again, we look at our problem in a model form. Since there's a series resistor Rx, our model will change slightly. This is still our 5 elements here, including the back EMF. Now we have a series resistor here. So we have now 5 components plus the back EMF. So we have 6 components which move then across these 2 terminals. And again, still the terminal current is equal to the field current is equal to the armature current, because this is still a series combination. So that's actually shown here. So going to the series resistor required here, we know this condition must apply. We have now again a new shaft speed, omega m2. I call it omega m2 here, which is then 50 radians per second. But we know since the shaft speed will change, the back EMF will change. Why? Because back EMF is related to the shaft speed. And since the motor constant is the same, because that is a constant, won't change, we will change our back EMF in order to have a 50 radians per second. So if I go and calculate the back EMF for this new condition of 50 radians per second, this was our motor constant, 2.24, 50 for our omega m2, then we will get 112 volts. So it is 2 times smaller than the previous case, because we just go from 100 radians per second to 50 radians per second. Looking to the problem, we need to have the shaft torque and also the terminal voltage unchanged. Now, in question A, we have determined that the shaft torque and also the developed torque were these values. If these are unchanged, according to question B, then the terminal current must be also unchanged. That means the terminal current or also the armature current are all 40 amps again. Because if this was changing, then the developed torque will change. So that is of course the condition to have also the 40 amps there. Because the developed torque is equal to motor constant times the armature current. So we cannot change the armature current because the developed torque must be the same, since the shaft torque will be the same. That's actually shown here. Okay, then we can again set up our Kirchhoff voltage law here, now including 1, 2, 3, 4, 5, 6 elements, because we have now additionally the Rx. Again, it's a series combination, all of the currents are exact same, and we know that 2 inductors will again disappear here because their reactance will be 0 for DC conditions. So we again lose these 2 elements. Now we can simplify this and again make just one current, just armature current, because it's also equal to field current. Now we have three resistors here, Rx, Ra, and also Rf. And we have now the new back EMF voltage here, and all terminal voltage is also shown here. If I now substitute the values here with the new back EMF voltage condition and also the current, which is again the same in the previous case, I have this expression. You can see that the Rx here is the unknown. Now simplifying this a little bit further, you can of course subtract from the left and the right hand side is 112. You will get 148 is equal to 40 times this Rx plus 0.9, which is of course the summation of these 2 resistors. Now moving on to Rx, the next step is then 148 over 40 and then minus 0.9. So I do 2 steps at once, and then we have, if you do the math here for yourself, very simplified form of course this, you will get 2.8 ohms. So we require a series resistor of 2.8 ohms in order to reduce the shaft speed from 100 radians per second to 50 radians per second. If you of course make this a little bit larger, let's say you make it 2.9 ohms, then of course this equation here will still be valid, but what will happen then to your shaft speed? That is actually a question. If you increase this, you will of course have less back EMF, because this will still the same, because the current is the same. If the back EMF is reducing, then the shaft speed will also reduce. So if you increase your series resistor, you will decrease your shaft speed. And if you make this 0, you will come back to 100 radians per second. That's actually the condition. Alright, this is the end of this example number 4 about the DC series motor, where we discussed the condition to have a reduction in the shaft speed and also how to calculate the torque of the shaft when there's a friction. And again, if you have any questions, please let me know and I will try to answer them as soon as possible. And don't forget to like and share this video so that we can reach more people. Thanks for your cooperation and see you next time. Take care.